Alright, in this portion of how to write a successful GSA grant proposal, we're going to be talking about how to make an effective figures. And effective figures are surely worth something. I don't know if it's 1,000,000 words or 1,000 words or maybe just 10 words. But let's talk about it. So a good figure helps you explain your research question. Your proposal must contain a figure. This is a great opportunity, and it's in the format is a PDF no larger than 5 megs. But the danger here is that you can't, the most effective figure won't just be a cut and paste job from a publication or your advisor's grant proposal. You really need to make it and tailor it specifically for this proposal and this study in order to minimize, in order to make it most effective. So let's look at some examples, or actually we're going to talk a little bit more. Okay, so what kind of figure is most effective? Well, the first question is what is the purpose of your figure? Is it to help explain some real complexity in your study and help you save some text in the body of the proposal itself? Is it a conceptual model that you're testing? Is it, two competing conceptual models that you can help explain with more clarity through a figure? Is it to highlight the impact of your research and really demonstrate why it's important? And then that really can help you decide what kind of figure might be most appropriate, whether it's a picture, a map, a conceptual model, a flowchart of your research plan. If this happened, or we're going to do this, and then if this is the outcome, we're going to do this other thing. But if this other thing is the outcome, this other option is the outcome, then we're going to do something else. So let's take a look at some. Wait, we're not actually looking at some examples. So once you've decided what kind of figure you want to build, you're gonna need to build and refine your figure. So you need to have a title to help orient your audience. You need to have the figure meet whatever that is. We've talked about that on the last slide. You need to have a caption. Legends and scale bars are really important, especially if you're showing a map or something complex. You want to annotate the figure to really highlight the key elements. Like, you want to make it as easy as possible for the reviewer to grasp the key point of the figure and understand why it's really important to helping explain your grant proposal. All the text should be easy to read. Axis labels should be easy to read. Legends should be easy to read. And this is part of why it's difficult to just copy and paste from a figure paper or from a grant proposal. So I would recommend printing it out on an 8.5 by 11 sheet and see if you can really see all of the text very easily. Alright, and then you can also, consider using colors to make understanding more intuitive. So let's look at some examples now. So I don't know if you work with X-ray diffraction. I do. These are all examples from my own figures. But this is I think a pretty difficult figure to grasp. Just by sort of starting to look at it. This is X-ray mineralogy, X-ray diffraction patterns as a function of depth and tailings. But you might have said that in the text of your proposal, but by the time I get here, I might not remember that. So this is exactly a cut and paste job right out of a paper. This might be actually more effective, where you say you're looking at mineral transformations as a function of depth by X-ray diffraction. I guess I should have added that this is X-ray diffraction. But see here, I've used colored boxes to highlight the contributions from different minerals, and then I've used colors in my figure caption to help explain what those colored boxes are. I know you can get all that information from the figure itself, but it just helps the audience or the reviewer to understand. You can see the sulfides being depleted as you move towards the surface, and then you can see the enrichment of these other secondary phases. So here's another. This is a picture. It's a good picture, I think, in that you can see that there's a lot of dust blowing around at the site at this location. You can see these poor people that are in Tyvek suits, and they're actually wearing respirators, and they're just being pelted by this dust. But maybe a more effective, maybe, and I think that that really speaks to the impact, but I think maybe what would be more impactful is to, start at the state scale and show that, this is a site in central Arizona. You can see that the mine tailings pile is very large. It's next to this, it's adjacent to the town. And then you can start to understand why having blowing dust on these tailings, which are highly contaminated with metals, might be important. And then so you're going all the way from sort of a map of the state scale to the site scale to the sort of field scale, and then all the way down to the to a soil pit. And I think the the figure caption is really key in sort of explaining why each of these is important. So here's another example from another project that I've worked on. You have these are micro X-ray fluorescence images. A scale bar is important not only for the scale of the images, but also in looking at what brown means low counts or low concentration. Green means high concentration. I've also shown correlation plots, so you don't really have to use your imagination about whether these things are spatially correlated. And then I've offered a little bit of an interpretation of what I think of what we believe that it means, that tellurium is clearly spatially correlated with sulfur, iron, and copper, which points to an association of tellurium with chalcopyrite. Another example. So this is Delamar, Nevada. It's a historic mine tailings, gold mine tailings that are enriched in tellurium. And so you can see here in part A we have a map showing where the site is. I'm using red to highlight where that the site is not Caliente or Las Vegas. I have a scale bar to show how large the state of Nevada is, and how far away Delamar is from Las Vegas. Pretty large population center. Then I have a picture of the site. You can see sort of that there's sparse vegetation. It looks like an arid type of probably a semi-arid type of environment. I'm showing that the two tailings piles that were sampled, and sort of talking about why they might be different. They clearly have sort of different, even from at this scale, you can see that there's a difference in the sort of physical and chemical properties. You see some sparse vegetation on the tailings in the foreground, and you see no vegetation on the tailings in the background, and you can see that the background tailings are kind of consolidated. They seem to have erosion going on, whereas these tailings in the foreground sort of look like a beach. So then also, I'm showing that we dug a pit in the unconsolidated tailings as a function of, so we're looking as a function of depth. We don't see a whole lot of color change, but these are the samples that I'm going to be characterizing in this study. So just another example. You can see we're looking at the tellurium speciation in these Delamar tailings, and so I'm showing an EH-pH diagram. Using, I say that I got the data from Grundler 2013, which is really important. If you use someone else's data, that's totally fine, but you want to cite where you got it. So this figure shows that, we're expecting that we're going to have sodium tellurite, or we're going to have some kind of tellurite phase at the site, because the pH ranges are shown in boxed in purple, in contact with and these are in contact with the atmosphere, so we're expecting results that are sort of right around that, for EH and pH, right around the intersection of the purple box and the diagonal line. But that's actually not what we see, which is exciting. We actually see that we believe that there's tellurium +6 at the site, and that so that's interesting. It's not what we expected and what we modeled, and so we want to investigate that more. So here's an example that's a conceptual model. You can see that we're talking about the formation of efflorescent salts where you have water coming in, um, filling pore water spaces, dissolving minerals, and then during a drying cycle, you have evaporation or evapotranspiration that are pulling those metal-rich pore waters to the surface, and continued evaporation results in the precipitation of very soluble and bioavailable metals. So this is another option. Um, but but you might be thinking, but I don't have any data yet. Where am I going to get how am I going to make one of these figures? Um, well, the answer is modify a figure from an important paper or from your advisor's grant. And if you're going to do that, you have to make sure that you cite where it's coming from. Just like I cited that the data that was used in the EH-PH diagram was from a paper. Just put at the end of your figure caption "modified after," and then use this, put your reference. I hope this has helped, and I hope to see much better figures next year. Good luck with your grant.